Components of an MRI machine. An MRI, magnetic resonance imaging, machine is a complex medical imaging device that uses a powerful magnetic field, radio waves, and a computer to produce detailed images of the inside of the body. Here's a breakdown of its main components. Magnet, the most critical component of an MRI system. The magnet creates a strong and stable magnetic field necessary for the imaging process. This field aligns the protons in the body, which are then manipulated by other components of the MRI to produce an image. Gradient coils. These coils are used to apply a variable magnetic field across the patient's body. By changing the magnetic field strength at different locations, the gradient coils help spatially encode the positions of the protons, which is crucial for creating a three-dimensional image. RF, radio frequency coils. These coils transmit radio frequency pulses into the body to disturb the alignment of the protons. When the RF pulse is turned off, the protons return to their original alignment, releasing energy that is detected by the RF coils. This signal is used to construct the image. Computer system. The computer controls the MRI machine and processes the signals received from the RF coils. It uses complex algorithms to convert these signals into images that can be interpreted by radiologists. Display. The processed images are displayed on a monitor, allowing the healthcare professionals to analyze them for diagnostic purposes. Electronic support system. This includes various subsystems that support the operation of the MRI, such as power supplies for the magnets and coils, cooling systems to maintain the temperature of the components, and the digital-to-analog converters that prepare the signals for processing by the computer. Pulse sequence controller. This component controls the timing and performance of the MRI system. It dictates when and how much gradient power is needed, as well as when the RF energy must be transmitted. Array processor, used for image reconstruction from the raw data. It applies the Fourier transform to convert the signal into an image that can be interpreted. Press scan. Before scanning, certain tasks must be done, like tuning the coil, shimming the magnetic field, setting the center frequency, and adjusting transmit and receiver attenuations. Proper tuning is essential for high-quality images. Each of these components plays a specific role in the overall function of the MRI machine, and their coordinated action is what allows for the production of high-resolution images of the body's internal structures. Understanding these components is crucial for both the safe operation of the MRI system and the quality of the images produced. Let's delve into more components of an MRI machine. Bore. This is the tunnel-like space within the magnet where the patient lies during the MRI scan. It's designed to accommodate the human body and is a critical part of the machine's structure. RF transmitter/receiver. These are part of the RF coils that transmit radio frequency pulses to the patient's body and receive the signals emitted by the body's protons in response. The quality of the images depends significantly on the performance of these components. Patient table. The table slides the patient into and out of the bore. Its position is adjustable to ensure that the specific body part being scanned is at the center of the magnetic field, known as the isocenter. Antenna. This sensitive device detects the RF signals emitted by the patient's body during the scan and feeds this information into the computer system for image processing. Digital-to-analog converter. DAC. This component converts digital instructions from the pulse sequence controller into an analog waveform that is then passed through the RF power amplifier. It's essential for the precise control of the MRI system. RF power amplifier. It amplifies the RF signals that are to be sent into the patient's body. This ensures that the signals are strong enough to produce a clear image. Permanent magnet. Some MRI machines use permanent magnets made from magnetized ceramic bricks. These create a strong magnetic field necessary for the imaging process and are designed to be large enough to comfortably fit a patient. Iron frame. In systems with permanent magnets, the iron frame supports the weight of the magnet and helps focus and constrain the magnetic field to the desired area. These components work together to create the detailed images that MRI is known for. The technology behind MRI is quite complex, and each part plays a specific role in ensuring the system functions correctly and safely. Let's explore additional components that are integral to the function of an MRI machine. Shim coils. These coils are used to correct inhomogeneities in the magnetic field. Since the uniformity of the magnetic field is crucial for high-quality images, shim coils make fine adjustments to ensure the field is as homogeneous as possible. RF shield. This is a barrier that prevents radio frequency noise from outside sources from interfering with the MRI signals. It ensures that only the RF signals generated by the MRI system and the patient's body are detected. RF power amplifier. This component amplifies the RF pulses that are sent into the patient's body. The amplified RF pulses are necessary to flip the spins of the hydrogen protons in the body to the correct angle for imaging. RF receiver. After the RF pulses are turned off, the protons in the body release energy as they relax back to their original alignment. The RF receiver detects this energy, which is then used to create the MRI images. Cooling system. High-field MRI magnets generate a significant amount of heat. The cooling system, often using liquid helium, is essential to keep the magnet at cryogenic temperatures and maintain superconductivity. Console. The console is the user interface for the MRI technologist. It includes the controls for operating the MRI machine, such as starting the scan, adjusting parameters, and monitoring the patient. Intercom system. Safety and communication with the patient are paramount during an MRI scan. The intercom system allows the technologist to communicate with the patient and ensure their comfort and safety throughout the procedure. Emergency stop button. For safety reasons, an emergency stop button is available to immediately halt the MRI scan in case of an emergency, ensuring the safety of the patient and staff. Faraday cage. The entire MRI scanning room acts as a Faraday cage, which is an enclosure used to block external static and non-static electric fields. It's an essential part of the RF shielding of the MRI suite. Power supply. The power supply provides the necessary electrical power to all components of the MRI system. It must be stable and reliable to ensure the proper functioning of the machine. These components, along with those previously mentioned, work in concert to enable the MRI machine to produce detailed images of the body's internal structures without using ionizing radiation. Here are additional components that play a role in the functioning of an MRI machine. Superconducting coils. These are used in the main magnet to create a strong magnetic field. They are cooled to cryogenic temperatures to reduce electrical resistance and allow for the maintenance of a high magnetic field with minimal power consumption. RF shielding. This is a protective measure to prevent external radiofrequency interference from affecting the MRI signals. It ensures the purity of the data collected during the scan. Control room. This is where the MRI technologist operates the scanner. It is usually shielded with RF shielding and has a window that allows the technologist to see the patient during the scan. Quench pipe. In the event of a quench, a rapid loss of superconductivity, this pipe safely vents the helium gas used for cooling the magnet outside the building. Siting. This refers to the location and construction specifics of the MRI suite. Proper siting is crucial to accommodate the magnetic field, reduce vibration, and ensure safety. Head coil. A type of RF coil specifically designed for brain imaging. It provides high-resolution images of the brain and is shaped to comfortably enclose the patient's head. Body coil. Another type of RF coil used for imaging larger areas of the body. It is built into the bore of the MRI machine and is used for transmitting and receiving signals. Surface coils. These are small RF coils placed close to the body part being imaged. They provide high-resolution images due to their proximity to the anatomy of interest. Phased array coils. These coils consist of multiple elements that can be used simultaneously to improve signal-to-noise ratio and accelerate image acquisition. Contrast injection system. Some MRI scans require the injection of a contrast agent to enhance the visibility of certain tissues. The system for this is often integrated into the MRI suite. Safety interlocks. These systems ensure that the MRI machine cannot operate under unsafe conditions, such as when the door to the scan room is open. Acoustic noise reduction features. MRI machines produce loud noises during operation. Modern machines include features to reduce this noise for patient comfort. These components, along with the primary ones like the magnet, gradient coils, RF coils, and computer systems, make up the complex and sophisticated technology of an MRI machine. Each plays a specific role in ensuring the quality of the images produced and the safety of the patients and staff. In MRI, T1 and T2 refer to different types of weighted images that highlight various tissues within the body based on their relaxation properties. Here's a simplified explanation. T1 weighted images, T1 timing, short TE, echo time, and TR, repetition time. Appearance. Fat appears white, water and other fluids appear dark. Use, excellent for visualizing anatomy and the structure of the brain, as well as detecting fatty tissue and marrow pathologies. Principle. T1 takes advantage of the differences in the T1 relaxation times of tissues, the time it takes for protons to realign with the magnetic field after the RF pulse is turned off. T2 weighted images, T2WI, timing, long TE and TR, appearance. Both fat and water appear white, making it easy to differentiate between the two when compared with T1WI, use, ideal for detecting pathological changes within tissues, such as inflammation, edema, or tumors, due to their high water content. Principle. T2WI is based on the T2 relaxation times of tissues, the time it takes for protons to lose phase coherence among themselves and stop producing a signal. In essence, T1WI is great for anatomical details and identifying fatty tissues, while T2WI is more sensitive to fluid-containing tissues and can better detect abnormalities. By comparing T1 and T2 images, radiologists can gain comprehensive insights into both the normal and abnormal conditions of the body's tissues.